Photonic thermometry can help transition the field of temperature metrology from resistance-based legacy technology to frequency-based measurements. The main advantage of this technique is that we can leverage advances in frequency metrology to make more precise measurements, whilst fabricating devices that overcome the physical limitations of current technologies such as size and sensitivity to mechanical shock and environmental changes.
The implication of this technique extends to changing how we realize, maintain, and disseminate the Kelvin in the United States and the world. An ultra-stable photonic thermometer will reduce the need for frequent recalibrations. Future development of optomechanical temperature standards can put a calibration standard in the user's hands, eliminating the need for specialized calibration facilities. Generally, individuals new to this method will struggle because it is an intersection of two divergent fields, both of whom have their own language, technology requirements, and specialized protocols for maximizing outcome. Any new user must learn to adapt and adjust to sometimes competing requirements.
To begin, clean an SOI wafer as described in the accompanying text protocol. Coat the wafer with 20 to 50 milliliters MA-N 2405 negative tone photoresist. Spin it at 4000 RPM for 60 seconds, and then transfer the wafer to a hot plate and bake it at 90 degrees Celsius for 15 minutes. After baking, expose the photoresist to the pattern shown here using a standard E-beam lithography setup. Then, place the wafer into MIF 319 developer solution and incubate.